Assalamualaikum warahmatullahi wabarakatuh. I be to all. Today we are going to present about vehicle engine. I will introduce my group member, which is me, Siti Maryam. We have Puteri Emilya and Hazeeq. So first of all, what is laws of thermodynamic and engine? The laws of thermodynamics play a pivotal role in determining how engines convert fuel into energy and motion. That means heat in, which is at a high temperature, will move to the low temperature, which is in the cold space. This is not about understanding of the laws, but it is also understanding the mechanic behind various types of engines. As the sentence says, the engine is the heart of your vehicle. It is a complex machine built to convert heat from burning gas into the force that turns the road wheels. For a logical idea, if you don't have fuel, you can't move your car or lorry or another vehicles. Okay, now, what is the difference between internal and external combustion engines in terms of thermodynamic process? To sum up this sentence, internal combustion means burning the fuel inside the system, which means heat engine that burns their fuel and takes combustion inside the cylinder. For example, is a two-stroke and four-stroke engine. For external combustion engine, that means is the heat from external sources. Heat engine that burn their fuel outside the engine cylinder. Energy developed during the combustion of fuel is transmitted to steam. The steam acts on the piston inside the cylinder. For example, is a railway steam engine. Next, we move to four-stroke engines. Most common internal combustion engine designed for motorized land transport which been used in automobiles. In this four-stroke engine, we have four important things, which is intake, compression, combustion, which is power, and the exhaust. Before that, you need to know about Otto cycle. The Otto cycle is the ideal cycle of the spark ignition, which is internal combustion reciprocating engines, and it consists of four internal reversible processes. For a four-stroke cycle, one complete cycle equal to four stroke, which is 2 revolutions. Next, we move to two-stroke engine. One complete cycle of two-stroke engine equal to 1 revolution. Unfortunately, two-stroke engines are generally less efficient than their four-stroke counterparts, but they are relatively simple and inexpensive, and they have high power-to-weight and power-to-volume ratio. Before we move to thermodynamic analysis, I'm sorry, Before we move to thermodynamic analysis, I want all of you know how engine works. So first, in the intake stroke, air fuel is drawn into the cylinder. Next, in the compression stroke, air fuel is compressed. For the combustion in third phase by spark plug, which is power stroke, and gas started to expand delivering work, and the last one exhaust stroke, which is residual gases are exhausted. This diagram shows Ideal auto-complete cycle, which is at the phase 1 to 2, is a isentropic compression. From 2 to 3 is a constant volume for heat transfer, which is Q in. Phase 3 to 4 is isentropic expansion, and the last one, from 4 to 1, is a constant volume heat rejection, which is Q out. From this analysis, we can find thermal efficiency of Otto cycle, which is equal to 1 minus 1 over R to the power of K minus 1, which is R is a compression ratio and K is a Cp over Cv. So we could continue with PV and TS diagram of Otto cycle. In SI engines, the compression ratio is limited by auto-ignition or engine knock. The PV and TS diagram actually same what as I explained just now, which is it consists of 4 internal reversible process, isentropic compression and expansion, and constant volume heat addition and heat rejection. That's all from me.
So for the next slide, me, Puteri, and Emilya will talk about most of thermodynamics and its application in engines. First law of thermodynamics. The definition of first law of thermodynamics is energy in an isolated system is constant. It implies energy conservation where the total energy of a system and its surroundings remain constant. For the application in engines, in a car engine, the chemical energy stored in petrol or diesel is converted into heat through combustion, and this heat energy is then transformed into mechanical work that propels the vehicle. For the second law of thermodynamics, the definition is the total entropy of any isolated system always tends to increase over time, reaching a maximum value. And the example is turbochargers recycle waste heat from the exhaust to boost engine power and efficiency. Third law of thermodynamics. As the temperature of a system approaches absolute zero, the entropy of the system approaches a constant minimum. For the example, cryogenic treatments of engine parts can result in decreased wear and tear and increased strength by reducing the system's entropy, thus indirectly impacting engine efficiency and longevity. Thermodynamics and engine efficiency. First is fuel quality, which is higher quality fuel can combust more completely, producing more power and less waste. Next is engine design, which is innovations in engine design such as variable valve timing can significantly reduce energy loss. Next is air-fuel ratio, which is the optimal mix of air and fuel leads to more efficient combustion cycles. And the last one is heat management, which is efficient heat management reduces energy waste and improves engine performance. For the example, Carnot efficiency sets an upper limit on the efficiency that any engine can achieve, dictated by the temperatures of the heat source and sink. So for the last one, I'm going to talk about strategies for enhancing engine efficiency through thermodynamics. First is improving combustion processes, which is advanced injection system and ignition timing can lead to more complete combustion. Next is waste heat recovery, which is using devices like turbochargers to reuse waste heat from exhaust gas will boost efficiency. And the next one is thermal insulation, which is reducing heat loss through better insulation techniques can enhance efficiency. And the last one is variable geometry turbines. This will allow for the adjustment of the engine's airflow, which is improving the efficiency at various speeds and loads. For an example is turbocharged engines, which is turbochargers use the engine's exhaust gas to drive a turbine, increasing the amount of air in the combustion chamber, and this process leads to more fuel being burned and consequently higher engine efficiency and power. That's all from
So today I will talk about the cooling system of the engine. The cooling system is an important part of an automobile engine. We must become more aware of this fact before making our car being overheat on the plus highway. The engine in your car works best at a high temperature. When the engine is cool, components wear out easily, emits more pollutants, and the engine becomes less efficient. Thus, another important task of the cooling system is to allow to engine warm up as quickly as possible and then remain constant engine temperature. There are three main components for engine cooling system, which is first radiator, thermostat, and water pump. Radiator consisting of many small tubes equipped with a honeycomb of fins to radiate heat rapidly, which receives and cools hot liquid from the engine, which is by basically it acts as a heat exchanger for the engine. Uh, so the second one is water pump, which keep engine cool by circulating coolant through the engine and radiator. This prevents engine from getting too hot and overheat. Water pump also have two main processes, which is circle and circulation, and also controlled by the thermostat. The third one is thermostat. Thermostat acts as a valve for the coolant and only allows it to pass through the radiator when a certain temperature has been exceeded. Thermostat also contains paraffin wax, which expands at a certain temperature and opens at that temperature. The cooling system uses a thermostat to regulate the normal operating temperature and of the internal combustion engine. When the engine reaches standard operating temperature, the thermostat is triggered, then the coolant can enter the radiator. In this slide, I will talk about the processes in the engine cooling system, which how can we maintain the temperature of the engine before from being overheat. So they are divided by six steps, which first heat generation, uh, First, heat generation. Second one's coolant circulation, heat absorption, heat transferred to the radiator, cooling in the radiator, and cooling recirculation. In heat generation, there are two processes, which is combustion and friction. Which is in the combustion part, the engine burns fuel to generate power, uh, and the process creates a lot of heat. Uh, and the friction part is moving parts within the engine also generate heat due to friction. So the second one, coolant circulation, which is consists of coolant and water pump. Which is coolant is a liquid that made of mixture of water and antifreeze that absorbs heat from the engine, and water pump circulates the coolant through the engine and cooling system. The third one is heat absorption, which is from the engine block. The coolant moves through channel in the engine block, absorbing heat from the metal parts. And the fourth one is heat transferred to radiator. They are consisting thermostat and radiator, which we know the thermostat is activated when the engine exceeded at some temperature, and radiator is the medium to release the heat from the coolant to the outside air. So the fifth one is cooling in the radiator, which consists of airflow and radiator fan. Airflow, as the car moves, air flows over the radiator fins, cooling the hot coolant inside. And the radiator fan, when the car is not moving fast enough, an electric fan help push air through the radiator. And the last one is coolant recirculation. Uh, After the coolant go through the radiator, uh, they maintain the temperature back and flows back to the engine to absorb more heat. And the expansion tank, a small reservoir that collects excess coolant and allows for the expansion and contraction as the coolant heats and cools.